with the recording getting ready to come on, if you have any personal questions, can you wait till after class until I turn off the recording? You're more welcome to submit any comments or anything that you're in need of discussing. Okay. So first of all, let's talk about what could potentially happen currently with the class. So in case I've just, so I'll say this, I received information about contact with a positive student. So the school procedures are to report that with the contact tracing so that the school is aware of it. And I was told at first to quarantine, and I got a call back, and I was told to report back to work. So I'm actually back on campus. However, I'm going to keep things closed with in-person contact until I get my results back. So I got tested this morning. My results should come in Friday, the latest Monday. So for the remaining of this week, there will be no in-person contact with me. So if you're in lab, you're just gonna we'll do something virtually. On the, I guess in the case that I'm negative, I'm gonna have to resume with labs and also allow the opportunity for students to still come to class if they like to. Keep in mind that you want to practice all the best practices for remaining safe, which is the social distance type of guidelines, 6 foot distance, mask, etc. Right. So I highly recommend that all students are keeping with those guidelines. Okay. If I do test positive, then you know that things will change dramatically. I'll probably will have no more in-person lab sections and no more in-person courses. That means everything will be done electronically, and I probably will not be able to report back to campus. So that means that you have to contact me exclusively through Teams. Okay. And in the case that something else happens where I start to deteriorate, that happens, and obviously the university has some things in order for that. But for the most part, I don't think I had direct contact to where I contracted anything. But to be safe, because I don't want students to not know my status, I wanted to go ahead and get tested, right? So if I was positive, you should know that. And if I'm negative, you also should know that. So I want to make sure that you guys know, and you would know all the information by the latest on Monday. So for now, I will not have any opportunities to meet me in person, but please try to schedule a time if you need to discuss with me via Teams. All right, keep in mind that scheduling system, this helps me become effective. All right, it's going to be really hard to manage if you calling and this person is calling, that person calling, all at the same time. There's no way that I can kind of be able to get to all those calls. But also at the same time, my office hours are dedicated for students, but there's other times of the day that I'm supposed to be doing things for the university as well. So I need that time as well to run here and there to do X, Y, and Z so that I can keep up with all the other meetings and things that I'm supposed to be doing. So if we can stay within that guideline of keeping true to the scheduling, then we'll be okay. All right. And just because of the sake of time, if there's any other questions students might have, if you guys can wait till after class, I can take those questions. Okay. Good. But I wanted to have that on recording so that all of us would know the plans for moving forward with the class. Okay, for a show of hands, if you can see my screen and hear me, would you mind sharing or just raising your hand? Should be a white screen. I'm going to teach live today, right? Just because of the circumstances, this is probably the best way to teach. All right, good. Looks like everyone can hear my screen. Let's go ahead and work on classification of reactive carbon species. All right, there's a new classification that we need to talk about, and then we're going to move into a lot of the chapter 6 information. All right, so when I use the word classification, can anyone tell me that has a mic? What am I really referring to here?
Is it primary, secondary, tertiary?
That's right. All right, I'm going to cover my first reactive intermediate, which is the radical. Thank you. That was dead on. I'm asking you, can you tell me the substitution pattern? Is it a primary, or methyl, or secondary, tertiary, etc., right? So for the most part, I think the class has that down, but let's just kind of keep working on that really quickly. So if I gave you this, I need to zoom in a little bit because I need to be able to try to get these the right size that I want. If I gave you this radical and I asked you to classify, you would tell me that this is a alpha radical, right? And if I gave you this radical, and let me change my settings, I'm so sorry. All right, somebody needs to join in. Get them in here shortly. If I gave you, this probably should have been a little bit smaller, but that's what I can do. If I gave you this radical, what would you tell me this radical would be classified as?
Is it ethyl radical?
Well, not necessarily that. I'm looking for the
Would
word
be a primary radical.
primary.
Secondary.
No, this one's primary, right? And I needed to, let me do this because I know I confused students on this one. I'm so sorry. I need to put my H's here. That's a methyl radical, but this will be a primary radical. If I gave you this radical here, what would you tell me this one is? Sorry, give me one sec. Just to put the dot in the right spot, you would tell me that is a what type of radical there?
A secondary
Yeah, this is
radical.
secondary. All right. And this radical here would be classified as what type of radical? I put the single electron on that central carbon. What would you tell me that is?
Tertiary radical.
That's a tertiary radical. Is there any questions so far with classifying radicals? All right.
What's the difference? What's the difference between the two in the middle?
Two in the middle. Which one? Like this
The
one?
primary and the secondary.
The primary and secondary is where, how many carbons are attached to the reactive carbon? So good question. So let's go ahead and let's try to work on that. So the way that you determine your classification is that first you need to find your functional group. And in this case here, we're describing radicals, right? So I'm going to put an arrow at all possible radicals, right? And then the question you should ask yourself is, how many carbons are attached to the indicated or to the, what's the best way to say this? To the desired, I guess, to the functional group, the functional carbon, we'll say that. Or what's even better to say really is the, let's say reactive of the functional carbon, all right? So that comes from the question that's asked. If I ask you to classify the radical, then you know that the functional carbon would be the radical carbon. But if I ask you to give the classification of an alkyl halide, then you know the carbon that has the alkyl halide or the carbon that has the halide will be the functional carbon. We'll try to do some examples of those shortly. All right. So if I had to look at these three cases, go ahead.
So you see on your last example, the tertiary radical, if that dot was at the top of that like the carbon going up, would that be like an isobutyl, an isopropyl? You can't have anything that's labeled like that.
Yeah, we don't classify radicals by the alkyl group. Sure, I mean when you want to like describe something to someone as like in conversation, like I have an isopropyl, isobutyl radical. Sure, yeah, if that dot was moved up to that top carbon, then that would be an isobutyl radical. But for the most part, the task really is just to classify it as primary, secondary, or tertiary.
Okay. Thank you. That was
And,
my question.
okay. And I should never ask you to draw a isobutyl radical. That's outside of the scope of what we're trying to learn right now. Okay, good. So a question came up. How do I know that this is primary versus that being secondary? All right. So I had to ask myself this question. How many carbons are attached? I didn't mean to make this so big. Let's bring this down a little bit. How many carbons are attached to the functional carbon? So I put an arrow to each functional carbon. And if I had to say how many carbons are attached to that functional carbon, what would you tell me? There's only one carbon right here attached, right?
Mm-hmm.
So because I only have that one carbon attached, and the word for one really is primary, and we know this is a primary radical, right? If I had to ask you how many carbons are attached to this reactive carbon right here in the dead center, what would you tell me?
2.
There's 2 of them, right? So there's a carbon to the right that's attached, and the one to the left as well is attached, right? So that makes that carbon a secondary radical. And if I ask for the tertiary, how many carbons are attached to that central carbon right there, you will tell me there's how many present?
3.
There's 3, right? One up top, and then obviously one to the left, and then one to the right. All right, so does that answer your question that came up on how do I differentiate between the primary and the secondary radical? Okay, looks like it did. Hoping so. Since I'm using line equal structure, just go ahead and keep all this line equal. Well, it's impossible to draw a methyl without drawing the H's there. So that a line is going to always indicate 2 carbons. Okay. So good. So I'm thinking everyone is growing comfortable with determining this. All right. So what happens now is that there's a new class of radicals that a new classification that we want to be familiar with. If I'm one away from a phenyl ring, all right, and the phenyl ring is actually just the benzene ring that's now converted into a cysteine ring. All right, so this big thing here, let's see if I can get this to color right. Okay, that'll work for the most part. This right here is a phenyl ring. And the abbreviation for phenyl, I'm probably going to be using that, so it's probably a good time now to introduce it, is pH. All right, so if you ever see me use pH, it's not an element, I'm describing a phenyl group. All right, so whenever I'm one away from the phenyl group, we call this a benzylic radical. Right? This is why we're working on this, because we need to recognize this radical now. There's something unique about it. And if I'm one away from a double bond, I'm going to be classified as a allylic radical. Right? So not only do I need to now know primary, secondary, tertiary radicals, but also I need to know benzylic versus allylic radicals. All right. And again, benzylic means next to phenyl. There. I think I completely lost that. All right, let's see if I can minimize that, get some color on that. And allylic means what? Can anybody tell me what does it mean to be allylic?
An allele? Not allele. Oh my gosh.
Next to a double bond, if you want to just simplify it.
Mm-hmm.
Okay. So it's a radical that had a double bond next door. Why do you think these are special?
Resonance.
Yeah, dead on. That's right. All right. I'm a electron next to a pi. I'm an electron next to pi, right? So that's a resonance scenario, right? So let's look at the potential resonance structures that can go out, right? So these two are special due to resonance. And this is why we want to be comfortable with these, right? And what's so beneficial to resonance? Can anybody tell me what resonance? All right, resonance is a delocalization that stabilizes things, right? So we already described a radical as being electron deficient, right? I don't have the electrons I need. So if I can delocalize my deficiency, right, or if I can spread my stress over multiples of carbons, that's going to be a better strategy for dealing with that than keeping everything on one carbon. This is going to be a little tough to do. I'll try my best to do it. All right, let's go ahead and try to work on these resonance structures really quickly. All right, so because there's a single electron and there's a pi bond, I have to describe the movement of 3 electrons, right? And why do I need to do that? The radical is 1 electron and the pi bond has 2 electrons, right? So in the first step of resonance here, my single electron is being pushed into the pi bond, right? And that's going to cause the pi bond to break and put electrons at the end of that pi bond, right? Which is very similar to the instructions for case 3, which is push your lone pair towards pi, break the pi, put electrons in the inner pi. So if I do that for my first resonance structure here, right, I'm going to generate this structure here, all right? This is going to happen again. If it, out of convenience, I'm not going to be able to draw all these arrows, all right? It looks like it's going to be tough. I can take some time later today and get your notes updated, all right? But this is going to delocalize itself again. And my radical is going to move there. All right, this is going to delocalize again. And my radical moves there. All right, and this is going to happen one more time. Well, now I have a radical back on that position there. Okay, so being next to a phenyl ring allows me to delocalize this radical on 3 carbons within the system, right? There's going to be 3 carbons within the 6-member ring, right? And keep in mind that this first structure and the last structure are not the same. And I think sometimes students have a tendency to say that these are the same. They're not. Let's take a look why. If you look here at this bond here on my right-hand side, I have a double bond to it up top and a double bond to it at the bottom. But if I look at the same bond here on the right, instead of having a double bond on the top and the bottom, I have a double bond right at that line, right? So that tells you that the double bonds have delocalized and they give a completely different structure, right? Should the radicals at the end or that benzylic position, or they're in a different, the overall pi bonds have moved, all right? So a benzylic radical has a potential for 4 new resonance structures. If I have my allylic system, go ahead and draw the allylic.
Dr. Cooper.
Go ahead.
I know you can't do the arrows, but can you like talk through you moving the radical on the other ones?
Yeah, so the pi bond delocalized up, right? So this single electron comes down, one of the pi electrons comes up, and the other one has to remain on that carbon. this is why you get a double bond here and a single bond here. All right, so maybe I'm just going to teach. Give me 1 sec to cover the allylic, and we'll go back and work on these systems. There's a trick maybe that can help with looking at how to draw resonance. I'll come back to that question. Good question. I think I'm looking at the allylic. I probably should have started there before I did this system. Okay, did it knock me out? All right, can you guys still see my screen? I have no clue what just happened. Is that yes or no?
No.
Yes.
Microsoft Teams. Oh yeah, there's.
Okay, I'm sorry. My screen just went out for a second and came back. All right, is everybody still there? Can you guys still see?
Yes.
Is there anybody that cannot see? Can you speak up now, please? All right, let's look at the allylic system. All right, I got a very similar scenario, right? I have this single electron that's meeting another single electron, and the pi bond is going to break to put electrons at the end. I know that looks very weird. That's not the way I would draw it. It's just going to be very hard to get the arrows to look that one. Give me 1 sec. Let's just make my own personal arrows. We change this one and we should be good to go. All right. So these two electrons are going to meet to make a new bond here. It's because it's already a single bond here, that's going to convert into a what? A double bond, right?
A double bond.
That's right. And my other electron from this pi bond is going to have to reside now on that terminal carbon. So if I take a look at the resonance from this pushing here, I have a single bond on that side and now a new double bond. And my radical is going to move from being on the right-hand side to now be on the left-hand side. All right, so the trick here for allylic systems, we'll stay zoom in, to try to help you guys out, is that allylic is always a 3-carbon system. All right, so I'm going to call that carbon 1, this is 2, this is 3. Let's go ahead and change the size of these real quick. I'll change the color. So carbon 1 initially had the radical, and carbons 2 and 3 had the double bond. But if I look at the resonance structure, what happens? Now carbon 3 has a radical and 1 and 2 has what? The double bond, right? So if you can keep track of which atom started off with the radical, and you know in the second structure it should have a double bond, and the third atom of that system should now have the dot, right? So I hope that helps.
I have a question.
Go ahead.
So I'm confused. What is the arrow, the one in the middle that's on carbon 2? What is that pointing to?
One on carbon 2. So this radical is meeting a single electron from this pi bond, and they're meeting at this bond to say they make a new bond here. So these two are saying make a bond between 1 and 2. that converts now into a double bond. And the single electron from
Dr. Coop, you're breaking up and you're very low in the microphone.
okay. I don't know what more I can do. And I'm hearing the echo now as well. Maybe the internet will clear up. Is it better now?
No, you still.
Okay, can you hear me now?
You're
Yes, we
You're
can hear you.
echoing.
Just echo.
All right, can you guys hear me now? Is it better?
Yes.
Okay. So I'm not too sure of the question that came, but somebody asked me the question about these arrows here, and I'll try to describe one more time. There's a single electron here, and then there's a pi electrons that have, so that's a pi bond that has two electrons. So one of the electrons from this pi bond and the single electron are going to make a bond here, right, between carbons 1 and 2. And the other electron in that bond, in this pi bond here, just resides on carbon 3. So now I get a single electron on carbon 3, and atoms 1 and 2 gain an additional pi bond. So now they have a double bond there. Does that help describe or help with that question? Yes or no? Okay, so if you guys look, whenever a radical is interacting with a pi bond, again, there's always going to be these three atoms interacting. So if I look up top here, atom 1 would be the radical carbon, and 2 and 3 are the pi bond. And if I look at the delocalization of that radical now, right? Now now the radical 3, right? And if I need to, I guess I need to put these back. This would be 1, 2. I'm going to grade these out because now this system is done, right? And there's a new 2 and 1 that could participate. And so now, instead of the radical on carbon 3, it's going to be on carbon 1, and I get a new pi bond. So let me go back. This is the original 2. This is the original 3. I'll grade these out. But again, this can delocalize over these 3 carbons. And so now I get a new radical on carbon 3 here. All right, just for the sake of time, I'm not going to try to keep going through that. But it's just a delocalization of 3 that involves 3 atoms, where the first atom has a radical that moves to the end of that chain. So now, instead of having a radical on carbon 1, my new radical is on carbon 3. And in between 1 and 2, instead of having a single bond, I should have a double bond. And instead of having a double bond between 2 and 3, I now have a single bond there. Okay? Does that help answer the question? But this can be gained through practice if you want to. This is a good exercise to try to draw the resonance structures here, right? Try to push the arrows to describe resonance. Okay. Any other questions? They were all good questions. All right. So when it comes to benzo and allylic systems, all right, we can actually have a more detailed description of things. So let's take a look at this radical here, if I can draw it. If I had to ask you to describe this radical, what would you tell me? Are you guys still there in teams, or I'm just talking to myself?
It'll be benzylic.
Could be a tertiary benzylic radical.
Yeah. So this is a tertiary. Very good. So everyone can see that's tertiary. It's benzylic, but it's triply benzylic. Why have I said the word triply here?
Because it's all 3 of those other forms.
Exactly. There's 3 benzylic carbons around, right? So it's benzylic by 3. That's why we say triply. All right, so that means that there's new descriptors that we can use. We can also say that something is triply or doubly, right? So let's take a look at something like this. But actually to describe this radical, what will you tell me? Sorry, I haven't put the dot yet, but it's going to go in the middle there. What will you say about this?
Doubly allylic benzylic radical.
Yeah, we get somewhere. It's good. Very, very good. All right, so this is a double allylic. It's definitely tertiary, so I'm going to say it's a tertiary radical. I hope everybody's comfortable with that. It's doubly allylic and benzylic. Are we comfortable with that so far? Yes, no?
Yes.
Okay, good. So now we're at a point of we need to classify stability. So the tertiary triply benzylic radical is the most stable radical on the planet. All right. Actually, that radical is we like to say is persistent, sub-persistent. That means that you can actually observe this.
Which one is it said again?
It's the triply benzylic. It's the most stable. This version right here. All right. Next would be the doubly then your regular benzylic, and a triply allylic, double allylic, single allylic, then your tertiary or your normal tertiary, secondary, primary methyl. Okay. And don't forget that all these in front, these have to all be tertiary. All right, so the take home point is that if I had to investigate the the benzyl versus the allylic radical, which one would be more stable? I hope you guys are getting comfortable with the fact that the benzylic radical is more stable. Can anybody tell me why that would be more stable?
Because it has more carbons that are attached.
It's not always by the more carbons. Can you give me another description?
Would it be the double bonds that it has within it?
Is it a double
More
bond?
resonance.
There we go. That's the word I'm looking for. It's the resonance structures that come out of it, right? So for the benzylic case, how many resonance structures did I get?
3.
A total of 5, right?
Oh.
But you got 4 new ones, right? 1, 2, 3, 4, for a total of 5 structures. For the allylic system, how many resonance structures total came out? It's 2 structures, right? You was able to just draw 1 new one, right? So because I generated more resonance structure, that tells me that I'm going to do a better job of stabilizing that single electron, right? Because that means it's delocalizing over more carbons, right? So instead of having only a total of 3 carbons, right, probably delocalizing over all potential carbons, right? So this is why the benzylic system is more stable. So when it comes down to really trying to break these things down here, right, a triply benzylic will be better than a triply what? Allylic system, right? Right. I think everybody's getting comfortable with that. Any questions currently? I can't believe my time is almost up. I didn't really do anything that I planned to do. All right, so we need to move right into our first big topic in chapter 6 is, I'm sorry, I'm trying to get my lines to be standard. All right, I have this compound here, and I reacted with Br2 with light. And I got 2 new potential products. I need to study these products really closely. All right, one of my products look like this. But my other product look like this. All right, so what in the world happened here? Okay. So can we explain how we got both of these products? Right? Can anybody give me any insight before we start to talk?
I don't really know how the double line got moved on the second one, but on the other one, she
Okay.
added the BR was like on a primary hydrogen, or not primary hydrogen, primary radical, and then the other one was on a tertiary radical.
Good. So the topic that comes up is allylic bromination, right? So now we know that we can brominate on the allylic position. All right, so this is the normal way at the basillic, and this comes through a allylic rearrangement. All right, and that word rearrangement is going to be big in this chapter. We're going to realize that our next group can also rearrange, which is carbon cations. We're going to start working on those soon. So let's try to break down what happens. All right. If we can do the mechanism, and this will be the end, hopefully, of today. If I can generate a question, we'll do that as well. All right. So what happens in this mechanism? I'm going to draw an H here. Is everybody comfortable that these are all A's? Right. There's only, again, to do a free radical halogenation, I have to have a what present on my carbon? And hydrogen, right? And the only carbons that have hydrogens are the ones that are indicated. Right? And they're all identical. Can everybody see that? Yes, no?
So
Right.
what are those?
How do I know they're identical? Because this is a carbon that has 3 H's that's attached to a carbon that's involved in a double bond, right? Same thing, attached to carbon double bond, 3 H's, carbon double bond, 3 H's double bond. So these are all identical, right? So these are the only potential carbons at first that can react. So I'm going to skip the initiation step. I'm hoping everybody's comfortable with that just for the sake of time. A bromine in the presence of light should do a homolytic cleavage to generate what? 2 Br radicals, right? Is everybody comfortable with that stuff? Can you guys do that mentally for me? In the notes that I released, I'll show how this forms, but the first step is forming this. The second step of every free radical halogenation should be a propagation step, right? All right, and I'm going to extract a hydrogen in my propagation step. That's going to generate this radical here. All right, I think everyone can see that. And if I terminate at this position with another Br radical, I get my first compound, right? But I should recognize that there's potential what for this molecule?
Resonance.
Resonance, that's right. So let's draw the resonance structure out. Again, we can use that 1, 2, 3 trick. If this is 1, 2, 3, now carbon 3 should have a what on it? A radical, and carbons 1 and 2 should have a double. That's right. Let's see if we can push the arrows for that amount of time that I have here. The structures are so small that I have to use specialized arrows. Try to get that to show. Oh boy. All right, this is not going to work in the time that I have. Let's just use chemistry's arrows if I can. All right. Sorry, these arrows look a little tough. Because all it's trying to say is that this single electron and one of the electrons of the pi bond make a double bond here, and the other electron of the pi bond resides in that carbon. All right, so now I get these two potential structures. And I realize that if I, actually, you know what? I'm going to erase these arrows. I just don't like the way they look for what we're trying to do now. But if I take my Br radical and terminate, let's have one of those things. Here we go. This terminates to that. And this compound now terminates to. Okay. So that's the take-home point now, is that allylic bromination has the potential to do this allylic rearrangement. So you want to keep that always in the back of your mind. Now, before we end, let's discard this really quickly. Which compound is the major product? Anybody help me out here?
Would it be the second one?
All right, let's take a look. So how do we determine which compound is major? I should go ahead and classify my radical intermediates, right? So if I had to classify this intermediate, what would you tell me here? I'll look at the carbon that's reactive.
It's primary. Primary.
Right? This one's primary, only has one carbon attached. Very, very good. So there's another word that we need to use. It's primary, but it's also way.
Allylic.
Allylic. All right, so this is primary allylic. And you want to be prepared for that, because I will ask you those questions on the next coming test. Can you fully classify it? This is primary allylic. Next door, what's the classification of this compound? Again,
Tertiary.
All right, that's going to be my reactive carbon. What was that? I'm so sorry.
Tertiary allylic.
Yeah, very good. This is a tertiary allylic substrate, or a radical, I'm sorry. Which is the best radical? And when I mean best, which one in terms of stability?
The tertiary allylic.
Yeah. The tertiary allylic compound is going to be the best. Oh, some people are trying to get in. I'm so sorry. All right, you guys should be in now. Yeah, tertiary allylic radical is the more stable radical. So because it's the most stable radical, it's going to lead to the what product? The major product. So that means that this product here is major. Any questions around that currently? Okay, no questions. Very, very good. I thought I asked for 5 pages. Did we go through all 5? All right, let's do some questions and we'll end today. Didn't do my request. Modify. All right, there's one little thing that I need to discuss, all right, before we start these problems. I'm just thinking about that because there's a lot of potential products that can form. All right, there is a reagent that specializes in these cases here. Which is for allylic. In this case, it's really a bromination. All right. We call this compound NBS. It stands for N-bromosuccinimide. Let's draw the structure of that compound really quickly. We'll talk about the mechanism around this. It's no different than the others, just a different structure that forms a radical. It's an N here. And there'll be a BR here. All right. This is the reagent that we prefer to use when we are trying to do a allylic halogenation, right? BR2, I2, and light, it has a tendency not to work always at the allylic position, right? So since now that we are aware of this type of chemistry, when we want to use it, we will substitute in this. This is the way that I'm saying to you guys for tests and exams, quizzes. If I want to do allylic bromination chemistry, then I want to use NBS. Okay, so let's do these last two examples so you guys can finish your day off. If I gave you this structure with NBS, and we do need light, and the same down here, NBS, light. You guys help me draw the major product, right? So let's draw So how would I start a question like this? I know NBS is going to specialize in what type of chemistry? Did I lose you guys in teams? Am I talking to myself? Hello? Hello?
You said what kind of chemistry is NBS?
Yeah, what is NBS is going to do? What does it specialize in?
Gonna break down that molecule.
I can't hear you clearly. I'm sorry.
I'm not sure.
Okay. Anyone else?
It has something to do with allylic.
Yeah, definitely. Okay, give me 1 sec. I'm trying to see if I can get the spelling right. I knew I misspelled this thing. It's instead of my. Did I get it right? CCINIM. Okay, I just had a I and a D. Okay, so this is going to do a chemistry that specializes in the basillic position. So we need to identify all basillic positions. All right, I can go there, I can go there, or I can go there. Actually, let me use a smaller arrow maybe. So can everybody recognize that these are the basilic positions? And again, what does basilic mean? Or allylic? I'm so sorry. This is not basilic in this case, but it's allylic. What does that mean to be allylic?
Next to a double bond.
One away from a double bond. That's right. So all these carbons are located one away. All right, it won't let me do but one arrow at a time. All right, so the way that I think about these problems is that first, I try to consider all the corresponding radicals.
Hey.
Hello, what's up? Okay, maybe somebody's not talking to me. That's fine. So I think of all the potential radicals. Give myself some room because I don't want to draw it on the product side. This is the thinking side. So I can have that radical. I could have this radical, and drawing the radical down there is identical. I'm hoping everybody, these two positions are the same. So these are the two potential radicals I can have, right? But don't forget that I can also have wet for each radical. So earlier I've been doing A, B, and C. Let's do that. So this is position A. Every allylic radical has a potential resonance structure. So you want to also mentally think about the resonance structure, right? So for this first compound, what is my resonance structure going to look like? Again, I'm going to use that 1, 2, 3 trick here, right? So now my carbon 3 is going to get a radical, which is going to be here, and my double bond is going to shift there, right? So these two potential products could form. And on the B side, what can happen? What is this resonance structure going to look like? I could also form a radical could go there, and my double bond will go here, right? So these are the 4 potential radicals that can form at these allylic positions. So I want to go ahead and classify these. This is going to help a lot in me determining which one will be the most favored to be formed. So this first radical will be classified as a primary allylic radical. I'm hoping everybody's comfortable with that. Moving a little bit faster because my time is up. This one is definitely a tertiary allylic system. Over here, this one is a secondary allylic system. And this one is also secondary allylic. So if I had to ask you which is preferred or which radical will lead to the major product, what will you tell me? Hopefully you should say that the tertiary allylic system will. This is going to be the most stable radical we have. So my final or my major product from this reaction should be where I terminate at that position, and I'm going to place a BR there. Right. This is going to be my major. Okay. And for the sake of time here, actually, I didn't want to, I made this question a little bit more difficult. I'm going to change it to that. And if I had to do this, these are going to be for all the potential benzylic sites, right? So I could go here or there, or I can do localized where there's a double bond here, right? And a radical there. So my answer here should be this compound. All right, and this last example is completely tricky because I made it up. There's some rules here you guys don't know. But for the rules that we've discussed so far, this would be the major product. There's another repeat with this one. We won't get to that until a different chapter. So this is going to be the major. And if you need to, we'll come to this on Friday to cover why did this end up becoming. I'm so sorry, I made a mistake here. Okay. Why did this end up becoming the major product? Okay. All right, I'm going to go ahead and end the recording for now. I hope this helps a little bit of how to answer these questions. Again, you want to go through your finding your allylic positions, drawing all potential resonance structures, indicating which radical is the most stable, and that's going to lead to the major product. And that's the same for this case here. Identify all potential radical structures, and I found the one that led to the major product. Okay, good. Very, very good. Let's go to teams and let's end the recording for today.